Hypothesis testing. Test hypotheses about a population proportion, and then test hypotheses about a population proportion using the binomial probability. Again, we're not going to focus as much of that. The reason why you use it, there's two things we do. If you think back to our conditions on being able to perform the test, what we talked about yesterday, what we talked about the day before in confidence intervals, one of the conditions we check for is normality. Is it approximately normal? If it's not normal and we don't meet some minimum qualifications of stuff, then what I need to do is I need to use a binomial distribution. And a binomial distribution was that binomial CDF that we did earlier on in a chapter before spring break, where that was primarily for the binomial distributions were skewed and stuff. The data was skewed in the calculation as you do it. So that's the alternative is if you don't meet the normal condition, can you still do a hypothesis test? Yes, you can. There's just other methods you go through to use to figure out your p-value. That way you can compare it to your alpha. So I believe we don't have many of those, if at all any. But that's what we end up doing is if you end up like if you're skewed and we have less than 30 and we have outliers, so then we go ahead and do a binomial probability distribution. Again, hypothesis testing basis. When observed results are unlikely under the assumption that the null hypothesis is true, we say the results is statistically significant. So that's a big one to kind of keep in mind as we do. When the results are unlikely under the suspicion that it's true, we reject the null. Two ways to determine is basically what's called the classical method or the p-value. The classical method involves using the z-score, using the z-table and creating your little bell-shaped curve and figuring out what these critical values are. And then does your p-value fall in one of the shaded zones based on what type of testing you're doing? And again, that is the classical method. We're trying to do everything with technology just to make things a little bit easier on us. Okay, so we're going to use the technology method is what we're going to do. But if you wanted to use the classical method, what you would do is you would go through and do your z alpha divided by 2, figure out what the z star is associated with the cutoff for the problem. What are these numbers right here? And then is your p-value in that range, one of the ranges based on what you're doing there. So again, those are your z-stars. Again, I'm not going to focus on using that, but there are videos out there if you want to use that one. If you chose that way, what we do is here is our z statistic. This is our little z statistic. It is different than the z-star. The z statistic is more or less a calculation of your sample proportion minus your hypothesized proportion. And then you divide it by the square root of the hypothesized proportion times 1 minus it, that portion, divided by it. Again, the bottom is your standard error. So, I have that down there in case we have any setups that we need to do, but I don't believe we have any of those that we're going to focus on. When we do the calculator feature, it actually tells us what that z statistic is, and I'll point that out to you. Where we come up with that z statistic. Again, when we calculate that z statistic, then we're going to try to figure out is that z statistic in a certain shaded zone? Is it in the shaded zone or not? Is what we're going to go after and try to find. If it's in the shaded zone, then we get to reject the null hypothesis. If it's not in the shaded zone, then we fail to reject. So we're going to focus on using this one here. This is the method we're going to focus on using, trying to find the p-value. Again, it also lets us know what the z-test statistic is. Again, all of our confidence intervals and our testing processes that we use are in that last column. When we hit stat, hit enter, hit stat, go over to the last column. That's where all of our test and intervals are. We're going to be doing a 1 prop z. We're doing a 1 proportion z test is what we're going to do. And then all we have to type in is the x value, the n value, choose the appropriate inequality symbol based on what's stated in the alternative hypothesis. And then again, based on yesterday's lesson, if the p-value is less than whatever the alpha is, we reject the null alpha hypothesis, meaning there is convincing evidence to support the claim in the alternative hypothesis. If the p-value is greater than whatever the alpha is, 1%, 5%, or 10%, we do not, or we fail to reject the null hypothesis. There is not convincing evidence to support the claim in the alternative hypothesis that's stated. So now here I just have, I think as we have a couple problems on your homework is kind of focused on trying to find the critical values for a right-tailed test regarding a population proportion at a alpha of 1% significance level. So as we do this, we would say, all right, I want to do an inverse norm. Sorry, issues with the we're going to do an inverse norm. Our area, again, as we're trying to figure out as we're trying to find out the z star, the critical value here is what we're trying to find. Again, based on our formula up above, it is the alpha divided by 2. So in this case, we would have 0.01 divided by 2. That would be our area. So what's 0.01 divided by 2? It's like 0.005, I believe. So we have inverse norm. The area is 0.005. Again, we're doing with z, so that means the mean is 0. The standard deviation is 1. And then let's grab our little handy-dandy calculator. And we're going to go second vars, inverse norm. My area is 0.005. And leave those alone. I am doing a left tail, so hit enter. And let's see. Oh, they're saying I'm doing a right tail, so never mind. Let's go over here to right tail. And is anybody using the older calculator where you don't have options for left or right? Out of curiosity. So I'm going to do a right tail and then go down and hit paste. The right tail just gives me the positive version. It tells me that my z statistic, my z star, gosh darn. My z star is 2.5758. So that would be if I drew that bell-shaped curve. We're doing a right tail, which means the right side is shaded, is what that means. And the z star for that is 0.25758. That's what that's telling us there. The z star there is that. So any z statistic, when we get done with that big fancy formula that I showed you, if we do that fancy formula and we compute it out and we get a z statistic that is bigger than 2.5758, then that's in the shaded zone, which would lead us to reject the null hypothesis. All right, so I'm going to write that down here real quickly. Just, if your z statistic this is the do not reject, and the shaded zone is the reject, the null hypothesis. So if your z statistic falls in the shaded zone, you reject the null hypothesis. If it falls in the unshaded zone, you don't. And again, that's if you choose the classical method, using that formula, getting your z statistic, and then using using your alpha to help create where your z star and kind of see, are you in the shaded zone or not. Again, we can do the same one for the next one, because I believe, again, you have a couple of these on your stuff. So I'm going to do 0.1 divided by 2 is 0.05. So I'm going to go ahead and take the alpha and divide it by 2. And then I'm going to do an inverse norm. My area is 0.05. My mean is 0, and my standard deviation is 1. And then we'll go second vars, inverse norm, 0.05. Leave the rest alone. What type of tail are we doing? We're doing a left tail. So we'll go down to left, hit enter. Go down to paste. And then my Z statistic here, and again, my Z star here is going to be a negative 1.6449. So now we would keep it in this case. We do keep the negative on there. So in this case, negative 1.6449. My shaded zone is to the left of that number. So if I get a Z statistic, if that formula, that fraction formula, works out to be a bigger negative than 1.6449, then I would reject the null hypothesis using the classical method. Remember, confidence intervals, we didn't care about the positive and negative symbol on the Z stars. However, on hypothesis testing, we have to keep those on there as we look at analyzing, do I reject or fail to reject? And again, this zone right there, we reject the HO. Here, we do not reject. Sorry, that was really thin pen. All right, so we're going to go through here. They asked us to test the hypotheses. I'm figuring you can probably do that next one if you wanted to by yourself. It is a two-tail, which, well, we should do it. Let's do it. Just because it's a two-tail. We have one of each in our notes. So 0.05 divided by 2 is 0.025. So I'm going to do an inverse norm. My area, 0.025. Mean is 0. Standard deviation is 1. And when I do that, it says not equal to, which is technically a center, is what that is. That is a center one. Not equal to is basically a two-tailed, so you have two shaded. So we would choose center here, and it's going to give me two values. It's going to give me okay. All right, so with that in mind, you guys get the same thing I got? Did you get those same numbers? Okay. And again, I get two tails means they're, if I fall in either shaded zone, doesn't matter. If I fall in either shaded zone, they're both a reject. Reject. I just have to fall in one of them. I can't fall in both of them at the same time, but if I fall in one of them, it's okay. And then again, the do not reject is in the middle. The fail to reject is in the middle. All right. So next part here, we're gonna work a few problems here, testing the hypothesis. Again, we can use the classical method, or we can use the p-value approach is using the technology. I'd rather just go ahead and use that if that's okay with you all. You all okay with using the TI-84 to get do the p-value approach? All right. So with that in mind, we are going to do a one prop z-test. And again, what I would, if you can do this for me, because I know I handed back the last test, do me a favor, and as I write down this script, when we do our test next week, please write down that. Some of you did, some of you didn't. You just wrote the number, and I still gave you credit. But it allows me to isolate where did you make a mistake. So some of you who wrote down the calculator script of what you typed in and you got the wrong answer, I was able to kind of highlight, okay, this is what you typed in wrong. And just for correction purposes for like the final, is just trying to give you some extra feedback on what you had the right idea, this was the only part that was wrong. And so that's why, so if you can do me a favor and keep writing down the script and what's in there, it'll help me critique you all to help us for the final going forward. It is what I want to try to make sure that's there. So we're doing a one prop z test. Again, when we do this, we get to type in I'm going to get the calculator version up here so we can see it on the screen. So stat over to test, down to option number 5, one prop z test, one proportion. So in this case here, as we start we'll write our little script here the way it's written on the screen, starting off with what is our hypothesized value? Well, the null hypothesis, the P naught is 0.3. So that's 0.3. Then we get to type in the X value. They say the X is 75. The N value is 200. So as I type those in, 0.3, and then we get to type in 75 and 200. Now, again, as you're using the calculator method, first off, the P naught, the very first number, has to be a decimal. If you're trying to type in something that's not, it's got to be a decimal smaller than 1, so because it's a percentage. So if you type it in a number bigger than 1, it's going to give you an error code. The second thing is the X and the N values cannot be decimals. They have to be normal whole numbers. So hopefully most of the time they give it to us. If they just give us a proportion, like they give us the P and they give us a total number of the sample, but they don't tell us how many, then we would have to multiply whatever that proportion is times our sample size and get that X value for what's going on in our problem. Okay? So I'm going to go through. They tell us that we're doing a greater than. So I'm going to go down and choose the last option. It's the third option. Greater than the null hypothesis value. I hit enter. Go down to, so as I did this, I chose that it was greater than the P naught is what I was doing. And then now I hit calculate, and there we go. So our P value is 0.0103. Our Z statistic, so the answer to that big fraction earlier on in the lesson, that Z statistic is 2.3146. Now they do tell me what P hat is. I don't need it. All right. So there's the information that I need. And again, we're using the p-value method, which means I'm going to use that very first answer right here. And I'm going to compare the p-value to our alpha. Okay, to the alpha. So 0.0103, and they told us the alpha was 5%. Is 0.0103, is it bigger than 5% or smaller than 5%? Is 0.01 smaller or bigger than 0.05? Smaller. So that would mean we would say it's smaller, it's less than. So again, whenever our p-value is less than, since p-value is less than our alpha, we reject the null hypothesis, the H sub O. We have convincing evidence. We have convincing evidence. To support the claim that the proportion is actually greater than 30% is what that's saying, based on that P being greater than 0.3. So here our P value after the calculation is less than the alpha that they asked us to compare it to. Since we're less, we reject the null hypothesis. We have convincing evidence to support that it's greater than 30%, because that's what it's saying up there for the alternative hypothesis. Now, if you chose to do the classical method and you found the Z star, the 2.3146 should be in the shaded zone when you go to do it. Okay, so again, it's your choice which one you want to use. I like using this one just because I think it's a little bit quicker. It's less steps to have to get to where we're doing. All right, let's try the next one. Again, they tell us that the null hypothesis is 60% versus an alternative hypothesis of being less than 60% or 0.6. They give us the X value. That's basically the X and the N is our P hat, is what that is. They create our P hat. We got to compare it to an alpha of 1%. So again, I'm going to do a 1 prop Z test. And again, my P naught is 0.6. My X is 124. My N is 250. And they told us that we're doing less than. So I'm going to go less than P naught is what I'm going to choose for my symbols. And then I'm going to go over to my calculator. Here we go. And hit stat over to test option number 5. And we're going to go with 0.6, 124, 250. And I want to choose the middle icon. That's less than the 0.6, less than the null hypothesis. Go down to calculate. And here I find out, again, I would always write down, okay, what is the Z statistic? The Z statistic is negative 3.3566, and the P value is 3.9461, but it has a E. That means times 10 to the negative 4 power. So that's actually 0.1230 3946. And that's what I got to compare to 1%. I have to compare that to 0.01. Well, technically 0.01 is greater than the 0.000003. So here we would do the same thing. We would reject the null hypothesis. Questions? So let's do a little sidebar. Let's just use our M&M data here, because these become calculator activities of going in there and just practicing, which I would highly recommend. I'd highly recommend going in, finding each one of those, and so forth, whether it's now or you do it in a minute. But let's do our little M&M's project, okay? So we gathered some data earlier on the internet. I did an internet research, and what it says that on the internet is that there is supposed to be 14%, or sorry, that's a horrible way to start a sentence. So you can tell I'm not an English teacher, right? So 14% of the M&Ms in a bag are supposed to be yellow. We are curious if this claim is true. Now, as we finish up, like right in our little thing, because before I put data down there and all this other stuff. Do you think it's actually that amount, or do you think do you want to say greater than, less than, or do you think it's just different? Do you think there's more yellows in there, less, or again, sometimes if you're not sure, it's safer to go with the different than, hey, it's different than what they publicize and stuff, because that gives us two areas that we can fall in. Because I don't know if you guys ever do this when you open up a bag of candy or something and you're like, man, I got a lot of this one color compared to these other colors. In this case, it might be easier just to say, hey, is it different than 14%? So we're doing like a two-tailed test. So we're wondering if that claim is true. So what we're going to do is we're going to do a hypothesis test. Sorry, my pen's haven't. Oh, I'm on the ears here, too. We will test the claim that the proportion of yellow is different from 14%. At let's go 5% significance level. When you construct a hypothesis test, you have to state what is the significance level, what is the alpha in advance before you actually do the process. Otherwise, it'd be cheating. If you did all the process, got the answer, then you got your p-value, then you're like, oh, I want to make sure that I reject it, so I'm going to change my alpha later on so it's going to be bigger than whatever the p-value is. So whenever you do a hypothesis test, you have to state what is the alpha in advance that you're comparing it to. That way we try to keep everything on the up and up and so forth. So, all right. So with this in mind, we have in our problem here, as we write our hypothesis statements, our null hypothesis would be that P is equal to 0.14. Our alternative hypothesis is P is different than 0.14. And again, if we defined what P was in a context, we would say where P is the true proportion of yellow M&Ms in a bag of M&Ms is what we would define P to be. We would want to go through the conditions for random. Was it random? I was in the store yesterday and I numbered all the bags with the Post-it note that were on the shelf of the same size. I used a random number generator to pick one of the bags out of random to do our experiment with. Okay. And so I tried to keep it random as much as possible. We also did a random choosing of the color prior is what we did as well there. So here is what we got for how many yellows for our class. In our class, we had 43 yellows. Our sample size for how many M&Ms were in the bag itself was 354 M&Ms total. And again, our alpha is 0.05. And so we're going to do a one proportion z-test assuming all the other conditions were true, that was random, it was independent, we meet the normal clause. Again, our sample size, again, we would have to do normal here. We would have to do 0.14 times 354 times 0.86 in order to check if we're normal, is what we'd have to go through and do. Is that greater than 10? I believe it is. So now with that in mind, let's do a one prop z-test. And again, our P naught is 0.14. That's what they publish. Our X is 43. Our N is 354. And we're doing the not equal to because we're saying it's different. It's different than 14%. So as I grab my calculator screen, there we go. And we're going to go stats over to one prop z-test. And we're going to go 0.14. And 43 were yellow out of 354. Again, that's a big difference in those two numbers there, so I'll be curious. Then my p-value, get down my which way am I going? Hit enter, and I hit the negative sign. Daggone it. I got to redo that. My apologies. Could have kept all the stuff. There we go. So in our problem here, our z statistics, so if we were doing the classical method, we'd be wanting that number, negative 1.0048. Our p-value is the 0.31498. Now they do tell us what the p-hat is. They do tell us that p-hat for our sample was 0.12146, so 12.15% of our bag was yellow. So now I would compare the 0.31, so 0.31498 is greater than 0.05. So since p-value is greater than the alpha, we failed to reject, or we failed to reject. We do not or we do, we fail to reject the null hypothesis. There is not convincing evidence to support the claim that the proportion of yellow M&Ms in a bag of M&Ms is different from 0.14. Again, based on the sample data that we had there, we do not have convincing evidence that it is different. I'd probably have to do some research, but they do say that it should be 14%. They don't put on the internet what the margin of error is, and so we could always compare it to a confidence interval. What is the true proportion? What is the confidence interval? Where is the true proportion of yellow M&Ms? What is it? With the margin of error. So right now, Well, we don't have convincing evidence. I mean, yes, our p-hat was less than 14%, but it wasn't significantly less. Okay, it wasn't tremendously less. It wasn't like we got a p-value of like, you know, 0.0002, or you know, something that was a lot smaller. I mean, this was bigger, so you know, it's within the realm that hey, it's reasonable that that percentage is correct. Is what we have here. So. Let's roll through a few more together of the confidence intervals, or of the hypothesis testing, sorry. So when throwing darts at at the stock pages to decide which companies to invest in could be a successful strategy. Suppose a researcher decides to test this theory and randomly chooses 100 companies to invest in. After 1 year, 53 of the companies were considered winners. That is, they outperformed other companies in the same investment class. To assess whether the dart picking strategy resulted in a majority of winners, the researcher tested the hypothesis of the null hypothesis being 50%, and then versus the alternative being greater than 50%. And they got a p-value, so they did the whole thing, got the p-value being 0.2743. Explain what this p-value means and write a conclusion for the researcher. So first off, do they state an alpha to compare it to? They don't. But if I think about the alphas that we mentioned in a previous lesson, an alpha of 0.01, an alpha of 0.05, and an alpha of 0.1, which is basically like 1%, 5%, and 10%. In all of those cases, what do we notice about that p-value? When you compare that 0.2743 to each one of those things, what do you notice? What do we notice between 0.27 and any one of those three decimals listed up above when you compare them? Is 0.27 greater than every single one of them? Yeah. So would you be making the same decision no matter what? So it really didn't matter that they didn't tell us an alpha, because again, the three most commonly alphas that are used, our p-value is way bigger than them. And so in that case, I'm going to be failing to reject. Okay, in all of these cases, we do not have convincing evidence. All our p-value here, again, as we look at our p-value, as we write up a little statement here, our p-value, 0.2743, is greater than any one of those alphas. It doesn't matter. It's greater than any one of those alphas, which means we would always be, we would fail to reject the null hypothesis. Again, that's the same thing as saying we do not reject the null hypothesis. Again, and by saying that we do not reject or we fail to reject, we do not have convincing evidence to support the claim. That the dart picking strategy resulted in a majority of the winners. That the dart picking strategy So there's our conclusion. again, we would just say, hey, it's just a nice little coincidence that that it actually, 53 out of 100, that was 53% picking winners. So it was just lucky that he got the majority of being winners by doing the dart picking method when he did his one sample. But it doesn't mean that we have convincing evidence to support that, hey, that's how we should do it. And then we're always going to pick the majority of the winners by that method. All right, so here's a little bit longer, intensive one here. The Kramer correct lens than half the time. So the website pundittracker.com keeps track of predictions made by individuals in finance, politics, sports, and entertainment. Jim Cramer is a famous TV financial personality and author. Pundit Tracker monitored 678 of his stock predictions, such as a recommendation to buy the stock, and found that 320 were correct predictions. Treat these 678 predictions as the random sample of all of Cramer's predictions. First off, determine the sample proportion of predictions Kramer got correct. So what would be the p-hat based on what's inside that problem, in that word problem? How can we figure out what p-hat is? What would I use as the ratio? Remember, p-hat is x divided by n. Yes, it's 320 divided by 678. So on a sidebar calculator, I'm going to go ahead and divide that out real quick. It's 320 divided by 678. And I'm going to take it out to 4 decimals. 0.47, wow, I'm going to go 5. 198, because the 7 made me go up to 20. So I'll take it out 5 there. So there's our p-hat. That's our sample proportion. Suppose that we want to check whether the evidence suggests Kramer is correct less than half the time. State the null and alternative hypothesis. So what is the H sub O and the H sub 1 based off of what they said right here? Our parameter is going to be P. We know the null hypothesis is it equal to. They use the terminology less than, so I know the alternative hypothesis has got to be a less than. And then in this case, they do say less than half the time. What decimal represents a half? Yeah, 50%. Now again, our p-hat, that number does not get used here. Our p-hat does not get used in the null and alternative hypothesis. It gets used later on in the calculation of stuff, but it does not get used in the null and alternative hypothesis. They say less than half the time, so that half the time is the 50%. Verify the normal model may be used for determining the p-value. So this is where we do the n times p times 1 minus p. Are you greater than or equal to 10? So is is n 678 times 0.5, and then 1 minus 0.5 is 0.5. Is that greater than or equal to 10? So is 678 times 0.5 times 0.5. That comes out to be 169.5. That is greater than 10, so we are normal. Yes, approximately normal, because we met that condition. And p 1 times 1 minus p is greater than 10. Again, in this whole unit we're working on right now, that's the process we go through for deciding if it's normal. Part D says draw a normal model with area representing the p-value shaded for this hypothesis test. With this in mind, so as I draw the normal model, we are doing a less than which means that I would do some vertical line to indicate where my Z star is. And I will, basically there's where my hopefully my p-value would fall inside there. Now we haven't calculated the p-value. We have not come up with, okay, what kind of alpha we're using. But since they didn't state it, we're gonna go with the default of 5%. And so to find the critical value here that's associated again with that, I would do an inverse norm, and I would do 0.05 divided by 2 for the area, so that's 0.025. It's going to be mean is 0, standard deviation is 1, and we are doing a left tail is what we're doing. So real quickly, second vars, inverse norm, 0.02501 left tail, and I get that my Z star for my critical value there is negative 1.9. It's 5996. So we'll just say negative 1.96. So that is the number here. So any Z statistic less than negative 1.96 puts me in the reject the null hypothesis. So there's our Z star. And then now they ask us to determine the p-value based on the model from part D. So we're going to go through and figure out what is the p-value using a one-prop z-test. So we're going to do a one-prop z-test. Again, our p sub naught is 0.5. Our x value we said was 320. Our n value was 678. And then we are doing less than the p naught. Is what symbol we're choosing. So again, as I grab the calculator on the screen, try to get that back up so you can see. Stat over to test, option number 5. 0.5 is my P naught, 320 over 678, choosing the one in the middle for the symbols. Go down to calculate, and here my p-value is 0.0722. That's my p-value. My Z statistic is negative 1.4594. So again, they didn't state a alpha, so we're going to use the default. What can we say about 0.0722 and 0.05? Which one's bigger? Yeah, that one's bigger there. So since we are bigger than our alpha, we do not. We fail to reject. We fail to reject the null hypothesis. There is not sufficient or convincing evidence to support the claim. Again, I have to go back and see what the claim is. Now, what I wanted to point out was when we look at the Z statistic, we had to draw the picture of the normal curve. And we found this number, negative 1.96. And we said if you fall in the shaded zone, here, we reject. If we fall in the non-shaded zone, we fail to reject. And so when we look at our Z statistic of a negative 1.45, technically a negative 1.45 is right here. There's a negative 1.4594. It is in this zone right there. Negative 1.49 or 145, 1.45, whatever it is. It is bigger than negative 1.66 in the sense of being it's a smaller negative. So it's technically in the fail to reject zone. Okay, so this was the first one we actually drew the picture with it to where I could show you that we would get the same interpretation whether we're looking at comparing the p-value to an alpha or comparing a p-value or the z-statistic, are you in the shaded zone, and so forth. Now, sidebar question, because they like to ask these kind of sidebar questions on there. Would your decision change? Would the decision change if alpha was equal to 0.01? Would you change your decision? If instead of using an alpha of 0.05, we use an alpha of 0.01, would we change our decision? What do you think? Again, we're comparing 0.0722 to 0.01. What inequality symbol should I put in there based on elementary days? Yeah, 0.07 is greater, right? So did our decision change? No, our decision wouldn't change. Decision would not change because, again, the alpha went down. Our p-value was still bigger than the alpha. So our decision would not change because p-value still greater than the alpha of 0.01. Extra follow-up question. What about a 0.1 alpha? What if we did a 0.1 alpha, which would be a 10%? Be a 10% alpha. Would my decision change, or would it still stay the same where I fail to reject? It would change why?
Because then the alpha's bigger than the p-value.
Yeah, our decision would change because, again, and sometimes, again, we need the concrete taking a look at it. If I write down my p-value of 0.0722 and my alpha is 0.1, that's technically that. Well, the alpha is now bigger. We switch signs. 7% is less than 10%. So in this case, our decision changes. Decision changes. We reject the null hypothesis. There is evidence to support the claim. Again, those are some of the questions they will ask at times. Is, hey, would if we use a different alpha, would you change your mind? Would it change our conclusion? We had the example earlier. If your p-value is bigger than 15%, or technically bigger than 10%, you're always failing to reject. Okay, no matter what your alpha is. It's just sometimes when your p-value is less than 10%, in some cases you fail to reject, some cases you reject. The smaller the p-value, like closer to 0.01 and below, then we're always rejecting. Okay, so there's, as we look at it. So, and depending on the context of the problem, dictates on whether it's like super serious and significant. Any questions on constructing that hypothesis test? Right. Again, your choice if you want to use the graphing method or the calculator method. I think the p-value calculator method is the easier one, especially at this stage of the game is where we're at. Trying to keep it simple. But if you'd rather use the formula and get the z-stat and then find the z-star, are you in the shaded zone or not? You can do that as well. So again, as I look at some of these other examples, I'll do some videos on these and put them in there because they asked us to. I'll do a video on those here. This is where when we look at real life stuff being used when we think about Lipitor. I remember I see commercials for Lipitor and Nexium stuff on the TV, and so that's where when we look at drug manufacturers and they're going through the trial stages and all that stuff, they're trying to decide hey, is it worth doing this? What are the side effects and so forth?